Good morning, everyone. I'm audible.
Yes.
Okay. So I hope you guys enjoyed the last session and have completed the assignments. Does anyone have any doubts from the last class? Since Sir is also here and the last class's speaker is also here. If you have any doubt, I would encourage you to first clear those doubts. Okay, so I'm assuming you guys don't have any doubts, or if you have any doubts, please feel free to put them in chat or unmute yourself. Okay. So for today's session, we'll be talking about what is cross-validation, ROC curve, and then we'll be understanding what is unsupervised learning. So without wasting any time, Supraja, uh, can we start?
Yeah, we can start.
Sure.
Good morning, all. Glad to have you all back. So today, as Abhinav said, we'll do cross-validation and supervised learning. I will be covering the theoretical aspect, and my friend Ritika will be covering the practical implementation of that. So we'll get started. Yeah, is my screen visible? Abhinav, can you confirm?
Yes.
Okay. So we're going to start with cross-validation. But before we know cross-validation, we need to know why we're doing cross-validation. So you need to know two terms, which is overfitting and underfitting. So what do you guys see over here? We see three students, A, B, C. Three students, A, B, C, and their respective hobbies are mentioned. Like student A's hobby is chatting, student B's hobby is to be best in the class, student C's hobby is to be learning new things. Student A is not at all interested in class, while student B mugs up everything the professor says, and student C is very eager to learn concepts. So now why am I putting this example? Because I want you to understand two things, which is overfitting, underfitting. This example will portray it better. So you have to remember these characteristics because I'll be asking some questions, and I would like to know that there is a bonus marks present this in this session. So whoever answers, they will be getting extra credits. So make sure you all answer because Ritika and I'll be noting down who are answering. So the more bonus points, the better it is for you. So we have three students, A, B, C, and their characteristics are mentioned over here. I hope all of you have seen this. Now, now basically the professor conducts a quiz based on whatever he thought. So he has conducted a class and he is conducting a quiz. So 30 minutes the class was taught and last 10 minutes quiz is being conducted. And some of the questions are repetitive like what is supervised learning, types of supervised learning, classification, regression, direct question. So direct question. So student A just guesses the answers and he gets 50%. So B, the person student B, who is very good in memorizing, who mugs up this, gets 98%. And then student C, who understands the logic and the problem solving approach, gets 92%. Now, now there is a quiz based on new unknown questions. Now let's assume that it's your final end semester. You have everything present. So now your guessing student as usual gets around 47%, while the person B who mugs up everything, that is the whole textbook, gets only 69%. And the person the student C, who goes by the problem solving approach, gets 89%. That is, he knows the underlying concept based on that he have applied. So here, when the teacher conducted a quiz on the known topic, basically there were some questions which were just known, like whatever the teacher had told in the class, the same question appeared. Here, there's a slight modification, maybe an application based. So C, who knew the approach, could get 89%, while B, who just mugged up, could not get it because it was the questions were not direct; they were little slightly twisted. While A, as usual, was just guessing, guessed 47%. So what I would like to infer from these three students is their performance. So A, who is not at all interested in learning, is underfit. That is, this is what we call underfitting. That is, the student A who was not at all interested in learning in the normal class test, by guessing, the person got 50%. And in the final end semester, the person got 47%. Then, when the person who loved memorizing the lessons in the class test, that is when the teacher taught everything, and then the class when the quiz was conducted and some of the questions were repetitive, got 98% because he mugged up everything the teacher told, but poorly performed in the final end semester test, which is 69%. While the person who had a conceptual learning performed well. Yeah. So this is what this is that was the best fit. So the person C had the best fit, while person A and person B are the examples of underfitting and overfitting. Now let me formally define you guys what overfitting and the example was clear, right? Everybody? Was the example clear? Please unmute your mic. Any doubts in the example? Guys, unmute. Any doubts in that? Okay, I'm assuming no doubts. So now let me tell you guys what exactly overfitting is. So when does overfitting happen? So overfitting happens when a model learns too much detail. So you can see that we have we have a area of house and the price of the house. So now we have now basically we have the model. This is the overfitted curve. So it basically the model has basically learned every even the smallest pattern. It has covered everything. So what is overfitting? So overfitting is basically when a model learns too much detail. It learns yep, so it too much detail every aspect. So here the way it covered this curve, it has covered almost every point. But so this will perform best. In a data set, we have the training data set and the testing. So in overfitting, what happens is the model will perform very well in the training, but it will poorly perform in the test, just like our student B, who memorized everything in the class, but poorly performed in the end semester. So the model will basically fit the training data perfectly, but it will fail on the new data, which is the test data. When slightly different new questions are given, it will fail. Then it has low bias and high variance. So maybe this might be a new terminology. I will be explaining it shortly. So what is low bias and high variance? So I will again explain it through an example. I love playing basketball. So let me take an example. So I am trying to throw a ball. I'm trying to throw the ball near the hoop. So what happens is low bias means, what does low bias means? Low bias means I know how to aim well. I know how to aim well. I know how to aim well, and most of my shots land near the hoop. And what is high variance? High variance is basically I miss the shot. I miss the shot wildly. That is, this is I'm the person over here, and this is the ball in my hand, and this is the hoop. So this is where my ball is supposed to go. So low bias means I know how to aim well, and most of my shots land near the hoop. High variance means I miss it wildly. That is, one shot goes too far, one is too short, the ball just drops over here. Another one is way off the slide. So there is no consistency. There is no consistency at all in my throws. So I've practiced a lot, but I don't have a steady hand. That is low bias. I have a good aim, but high variance. That means inconsistency results. Now let me talk in machine learning language. That is, a model with low bias and high variance is like it learns too well. It learns too well in my training data. That is, good accuracy is present in the training data, but poorly performs on the new data. That is, it is too sensitive to small details, just like my inconsistent throws. Is it clear? So that is this. Then this it captures all, like then the data is found to be overfitting. It'll capture all the noise, everything. Basically, here it was trying to capture all the intricate details, but this is understood that it is overfitting. So this is overfitting. Now let me talk about underfitting. So underfitting is basically like, let me show you visually through a graph. This is underfitting. So as I told you, this is the area based on the area of house and price of the house. We have we have points over here. Underfitted, it hasn't learned any pattern. It's just this line. The model can't do anything. That is, it performs poorly. Poorly both on training and testing. There in overfitting, what used to happen? It used to perform well on training and poorly on testing. But here it performs worse in both in training and testing. So it couldn't capture the underlying patterns at all. Here before in under overfitting, what happened? It tried to capture all the pattern. But here it's absolutely just a straight line. Here it has high bias, low variance, just the opposite of that. Poor performance in training and testing, as I had said. So now let's see in classification and regression. I've put on the chart here. So if I think what happened, so basically try to cover the whole pattern. But this is the right fit. Even though there are some outliers, it doesn't matter. Here underfitting is absolutely performing pathetically. Regression, again, the same thing. So we have continuous values over here. This is the right fit and this is the underfit. I hope it's clear. Now let me come to what is cross-validation, the main session overview. As the first thing you would have seen is cross-validation. So now what exactly is this cross-validation? So cross-validation is a technique in ML where we use to evaluate the performance. So this is used to evaluate the performance, the model's performance by splitting the data set into this thing. So we had done this by because the our model was either basically it was performing overfitting or underfitting. So prevent that, we are doing cross validation. It is a method, it's a technique which is used to evaluate the model's performance. So it'll basically what we'll be doing in this is we'll be splitting the data set into multiple parts. So we'll be splitting the data set into multiple parts. Then we'll train and test on certain parts. And as I had earlier said, it can be used to detect overfitting and underfitting, and it can generalize. The model will be able to have the capacity to generalize. This is what is the basic idea of cross-validation. It is basically a technique in ML which is used to evaluate the performance of a model. How? By splitting the data set into multiple parts. So we'll be training the model on some parts. So training will happen on some parts and testing will happen on the remaining parts. On the remaining parts. So, and how it'll be continued? Yes, the process will be continued multiple times to ensure we make the model more reliable, and the model shouldn't be biased. This biased model shouldn't be biased. Okay, this is what is cross-validation in simple words. So as I covered throughout the end of the session, you will be very clear about what cross-validation is. So now this is how our data set usually, how do we, as I said, we are going to split the data set. So usually we have the training set and the test set. So we have the 80 is to 20, 80% to the training and 20% to the testing. So there are different types of cross validations. So we have the K-fold, then we have the stratified, stratified K-fold. Then we have one more called leave one out cross validation. Okay, so we'll be seeing everything now. What is K-fold, what is stratified, what is leave one out cross validation. This is a general overview. Our data set is split into training set, testing set. So training is usually 80-20, or you can even keep it as 70-30. Yeah. So here I'll consider 80-20. Yeah. So now what is K-fold? K-fold cross validation. So let us imagine that I have 1,000 data points. 1,000 data points, and I want to check how well my machine learning performs on the new data. So instead of splitting the data directly into this, I'm not directly splitting into training and testing. So what happens is I'm splitting this 1,000 data points. What I'm doing is I'm not splitting the data at once at all. So what I'm doing, I'm going to use this K-fold cross validation method. So the K-fold cross validation will split the data into multiple parts. That is called the folds. Multiple parts. Here I'll be calling it as folds. Now what happens is, so when I'm splitting this data into multiple parts to test the model multiple times. So now how does this method work? So let us choose number k equal to 5. So k equal to 5 means 5 folds. I'm doing 5 folds. We're splitting the data into k equal folds, that is 5 folds. And we are splitting the data set into k equal folds. You can see here 1, 2, 3, 4. There are 5 folds present over here. Now for each fold, I'll be using k1 folds for the training. So initially what I'll be doing, I'll assume that this is our testing data and the remaining is the training. This is what I'm doing in the first thing. In the first, I've split it into 5 folds. How do I start? I assume that this portion is for the testing and the remaining is for training. Next, I assume that the second portion is for the testing part and the remaining is for the training part. So that there will be no bias over here. Otherwise, what usually happens, the first thing is first 80 is for the training and the rest is for the testing. But here, when you see, there will be no bias. So the first, when I'm splitting into k folds, what happens is I'm splitting the data into k equal folds, and each fold, one part will be for testing, and the remaining part is for the training. So you can see here for 5 folds, each of these, you can see this red color, which is the testing data, and the blue is the training set. So for I'm when I'm doing this after testing on all 5 folds, then we will calculate the average accuracy to get a reliable estimate of how. So now why am I using this k fold? Because I'm getting a more reliable evaluation, because I've used all the data. Here I've used this data for training, I've used this data, I've used this data. So here all the data has been used for both training and testing. And here this k fold it reduces the bias. It reduces the bias. There will be no dependence on a there will be no dependency at all on a single train test split, and it works for small data sets. Unlike a simple train test, only all data gets used efficiently. Here it will work for small data set. I hope it's clear. Let me just again sum up. What I'm doing is in k-fold cross validation, what happens exactly is I'm splitting the data into multiple parts. I'm splitting the data into multiple. I will write on the next page. So here what happens is the data. The data is split. Rather than splitting it only once into training and testing, TR and TE, rather than just splitting it once, I'm splitting the data split into multiple parts. Multiple parts. Multiple parts to test the model multiple times. And how does it work? So initially I will choose a number k. I will choose a number k. The example I took was k equal to 5. Means 5 volts. Then next is I will split the data set into k equal folds. So when I said 5, 5 equal folds. K equal parts. K equal parts means I'll split the data set into k folds. That is what I mean. Then for each fold, what I will be doing, I will use k minus 1 fold for the training. For the training, and I will use that 1 fold for the testing. This is what happens. This is the overview. The data set is split into multiple parts. I will choose a number k. So k equal to 5 means you will have 5 folds. Then I will split the data set into k equal folds. Then I will use the k minus 1 folds for the training purpose and that 1 fold for the testing. And then what I will do, I will average the result from all the k tests to get the final performance score. This is what happens. Okay. Now let us look at stratified k-fold cross-validation. Was k-fold validation clear? Can I get at least okay in chat box? Was it clear? Okay, let me go to stratified k-fold validation. So what happens is what is stratified k-fold cross-validation? So let me imagine that a data set where 90% of okay, let me take the other slide and then explain. Yeah. So let me imagine that 90% of the data, 90% of this data of my data belongs to class A, and then 10% is for the class B. So what does this say? This is a imbalanced data. So if I randomly split the data into k folds, some folds might not have enough. So if I try to do this using k fold, what will happen? Will it work properly? So what happens is it will work, but some folds might not have enough class for B. Some fold will not for this class B. What will happen is some folds might not have enough class B examples because we have only 10%. So class B might not have enough, which will lead to biased results. I hope you're getting what I'm saying. So we have the 90% of our data which belongs to class A and remaining 10% belongs to class B. Now, I randomly split the data into k folds. But now what is the problem? K-fold will work. Absolutely, it'll work. But what will the problem arise? So the problem will be that we do not have enough examples of class B, which will lead to biased results. That is where stratified k-fold comes into role. So what happens here? Here each fold has some property for each fold. Now again, now we have done this thing. K equal to 5. Again, we'll choose k equal to 5. It's the same thing as the first step as k fold. What will happen is here each fold has some proportion has some proportion of each class. That was not the case with K4. What I mean is, if you see through the visual diagram of here we have three classes, some brown color and yellow color and blue color. You can see that every folder has some proportion of each class. You get what I'm saying? This is stratified k-fold. So what does this stratified k-fold does is, this will ensure that each of these are our folds, whatever these red lines which I'm drawing, these are our folds. Each fold will have some proportion of each class as the original data set. So this way, are all the folds are so all these folds are basically representatives, are representatives of the entire data set. Entire data set. So this will basically make our model evaluation. What will become of our model evaluation? Make it more reliable. Make it more reliable. So let us see how this works. Too much theory. Now let us go to the explanation. So first, initially I chose k equal to 5. So I have divided the data set into how many parts? 5 parts. 1, 2, 3, 4, 5. 5 parts. Now I will ensure, let me erase some things. Okay, I'm not able to erase. Okay, yeah. So now what will happen is I will divide the data. I've divided the data into 5 folds. Now I will make sure that each fold has some percentage. So I've ensured that now this is the testing data. I've made sure the testing data has some percentage of each class as in the original data set. Okay. Now I'll perform k-fold cross validation normally. The only step which was added over here is, first step k equal to 5 was the same. Next was divided into k fold. That was also same. But here the third step was to ensure that each fold had some percentage of each class. That was my aim. That is why we shifted to, it is k-fold itself, but it's stratified. That is, we had some proportion of each class as in the original data set. So I make sure that each fold has some percentage of each class. Then I perform k-fold cross validation normally. I again train on k minus 1. Okay, this is k minus 1 is for training, and that 1 is there is for the testing. Okay. So let me take an example. So like example here for the let me take imbalance data set 80% and 20%. Okay, 80-20. So class A is 80% and class B is 20%. So now let's see fold for class A percentage. This is an example which I'm giving you guys. Class B. So let's go for 5 folds. How many folds we have? We have 5 folds. 1, 2, 3, 4, and 5. Now class A is 80%, 20%. 80%, 20%. This is the same thing. Now, if you use normal k-fold, what I had told you guys, normal k-fold, here some folds might have too many A's. So the problem with this was too many A's and too few B's. So this whole thing, if I do k-fold, it will lead us to poor evaluation. That is why stratified came into picture, where I will basically make sure that I take some proportion which belongs to each class so as to the original data set. So now let me tell you this thing. It will basically, the pros of this is basically it will better model evaluation. Then it will reduce the bias. Yes, this was this example. Reduce the bias, and it works really well with imbalanced data set. So that was it about the stratified. Where do I use this stratified this thing? What kind of problems? I already told you we use it in imbalanced data set. So we'll be using this stratify this thing for the classification problem. Example, the fraud detection, medical diagnosis, and etc. Now let us look at another method which is of cross validation is leave one out. LOOCV. Leave one out cross validation. So let me go to this page. Yes. So we'll talk about LOOCV. Leave one out cross validation. Let us imagine we have 100 data points. 100 data points in my data set, and I want to train a model. But rather instead of splitting into the conventional way of training and testing, what I do is I decide to use every every data point. Any doubts? Anybody? But instead of splitting into the conventional way of training and testing, what I do here in this method is I use every data point for training, except one, and test on the and test on that single left out point. So 100 data points means I will train my this thing on 99 and the remaining one on the test. Got my point? So in well, LOOCV, where it is used is instead of doing conventional way of training and testing, what I do is every data point that is present in our data set, I'm using it for training, except that one which will I'll be using that for testing out. So how let us see how it works step by step. Now I will pick a data point. First I'll pick a particular data point. I'll pick a one. Okay, I will pick one data point and I will set it aside. Let me set it aside. This why am I setting it aside? For my test set. What I've done, first step, what I've done is I have picked one data point and set it aside for the test set. Next, what I'll be doing is I will be training the model. I will be training the model on the remaining 99, which I had told you guys earlier. Training the model on the REMS remaining 99 data points. This is what I'll be doing. I repeat, I picked out one data point and I have set it aside for the test set. Next step is I have trained the models on the remaining 99 data points. Now third step will be what? I've trained the model. Now I have to test the model. Test model. How will I test the model? I will test the model on the single data point which I had initially set aside. Data point. Okay. In data point I left initially. And I will record the error. I hope my handwriting is fine. Please let me know if you are not able to understand anything. Yeah. So what I'll be doing? I will be doing this process 100 times. I, I will be doing it 100 times. Why? Because I have 100 data points. Now what I am making sure that I have to do the training and testing properly, right? So I have picked out one data point, set it aside. Then I have trained the model on the remaining 99. Then testing has happened on that one particular point which I had initially. I have to do this because each time I've left out one point, I have to cover all the remaining points. That is why I will be repeating this process 100 times because each time I had left out a different data point. Initially, I considered, suppose let's take 100 points over here, 100 points. So initially, I had left out one point, suppose the third point. So all the other points are considered for training. Next time, fourth point. Next time, fifth. So I'm doing this so that I can cover out all the different data points which I had left out. Next, last step will be basically I will average all the errors to get the final performance. This is what I am doing. Let me give you a gist again. What I done initially. Initially, I had picked one data point, and I have set it aside as the test set. Next, what I have done, I have trained the model on the remaining 99 data points. Now I have to test the model. Test the model will happen of what? For these 99? No. For the point which I had initially in step 1 I had set aside. So I will test that. Now I have to do the same process. I have to keep repeating the process 100 times. Why 100? Because in my data set I had 100 data points. I am doing this because each time I left out a different data point. Finally, what is the fifth step? It is averaging out all the errors to get the final performance score. Now let me tell you what are the pros of using this and the cons also. So the pros are basically, let me add a slide, 1 minute. Hmm. Yeah. So let me write it over here. So what was the pros of LOOCV? So it uses almost all data, right? It uses all data for training, all data for training. So it will give us, it is basically leading us to more reliable estimate. So here I'm getting a reliable estimate over here because I've almost used all data for training. And this LOCC works well for small data sets where every data point, now I've taken only 100, right? 100 data points as my example. So it works well for small data set where every data point is valuable. Every data, 100 data points, each point was valuable. Now, what is the consequence of this? I think you all can guess. Yeah, can anybody tell me what is the consequence of LOCV? Yep, I would like to hear your answers. Yeah. What is the consequence? Yeah, students, can you answer me what is the consequence of this? I told it works well for small data points. Yeah, I've almost given you the whole answer. Anybody?
Overfitting.
Not overfitting. I told you it works small for small data set. First, let me cover like it. What will happen if it this overfitting will happen? Correct. Yeah. Then will it work for large data set? If I had 1 lakh points, will it work properly? Will it work properly if I have 1 lakh points? Can I train the model 1 lakh times? Is it possible? Yes or no? Should I pick people out here? Yeah, tell me. Will it work? Will it work for 1 lakh data points? 1 lakh data points means how many times you have to train the model? Anybody? Anybody? It's a simple question. If I have 1 lakh data points, how many times do I train the model? 1 lakh times, right? Yeah. And next one, well, somebody told you this thing, overfitting. Because overfitting, why? Because it has high variance. So each time the training set is very similar, so the model will not generalize well. Okay, correct. Okay, let me continue. Yeah. So what was the pros? Pros was it had almost taken all the data for training and it works well for similar. But if I had 1 lakh points, that means I have to train the model this many times. Another thing is high variance. High variance means what? Each time training set is very similar. Right? Only one point I'm leaving out, right? So each time the training set is very similar, so the model will not generalize well. Okay? It will not at all generalize well. Okay? So this was about this cross validation. Any doubts for anybody? Yeah? Any doubts? Anybody has any doubts? We'll start the next topic now. Any doubts? Anybody? Cross validation. Abhinav shall, yeah, I think now Ritika can explain the practical part.
Sure.
Yeah.
Thank you, Supraja. Before I move forward, I would share the files up here so that you guys can access the code files. Just a minute. Yeah. Is my screen visible?
Yes.
Okay. So, as Supraja mentioned before, we'll be moving forward with the code part of behind cross validation. What is a traditional method that we follow? We have a training set, we have a testing, and we have a validation. This is in detail explained by Supraja, but let's see further of how we actually deploy them and try using them with real life values and structures that are present. So first, instead of moving into a data set, let's see how we work them with normal range of values. To do so, first we're loading up some modules. From the sklearn module, that library, we are choosing the K4, stratify K4 and train split. These are the things that we'll be working forward. The dataset that we're using today in the further course would be the load iris. Iris dataset is a flower dataset. It consists of 3 different types of flowers. We'll be looking into them in detail as we progress further. Next, we have the model that is the logistic regression. As seen in the previous class, you guys all know that logistic regression is a classification model that we will be using over here to classify the different flowers over here. To test how a model is performing, we will be using accuracy score and classification report. In the same hand, we will be using as well matplotlib and seaborn for visualizing how this cross validation takes place. And for manipulation tools, we'll be using pandas and numpy. Starting off which, let's consider numbers from 1 to 25. These are values from 1 to 25 and we are going to perform a cross validation on this. So as Supraja mentioned, we'll divide them into K4s. This will be my training and my K minus 1, that is the last value that is present, will be my testing. So now I'm going to do 2 types of K4s over here. First type of K4 is where I'm going to create 5 fours and 3 fours. So I'm going to split the entire dataset into 5 subsets and split the next dataset into 3 subsets. How am I doing this? I'm keeping a split ratio. This ratio nothing but tells us by how many times we're going to split that data and what is shuffle over here. So if I'm splitting the data, consider that this is nothing but my value. I would explain in detail what it is, but if these are my values, I'm saying that the first 10 values I want for training, the next 20 values I want for testing. I want this split to remain constant and the training testing is not supposed to be combined with each other. To make sure that these values are remaining together in the same order, I'm keeping shuffle is equal to false. So I'm creating 2 fours over here as mentioned. I have the first fold as 5 and the second fold as 3. But what are these 5 and 3 and how do we visualize it? So for that, let us try visualizing what these folds are. Now from this K5 fold, we will be able to split. So what are we doing from the K5? We have the train index and the test index. We're splitting these values and what is Rn? Rn is my entire range of values from 1 to 25. So what are we doing over here is we're initializing the train values over here from 0 to 8. These are the indices, not the values. When I have the indices from 0 to 8, that will be my training. I'm fixing the training. I'm telling all the remaining values to be my testing. Similarly, I'm telling from 9 to 16. These will be my testing data. My remaining indices, the index of these values will be my testing data. Plus, what is one thing that we can see over here? My testing values are from 0 to 7. Then I'm jumping to my testing. Then I'm doing training. In the similar way, I'm fixing 7 to 24 is nothing but my testing. The remaining values are my training. So it's not that I'm just considering like the first 5 values are testing and the remaining values are training. No, I'm doing an equal split of this in such a way that I have first 0 to the 16 values over here and similarly this. So it's like in such a manner that we want our data to be equally spread and to not be contaminated in one region or area. So we see that each of the row represents one iteration and the test set, these values, the second array that we can see over here, this is nothing but my test set. The remaining values are my training set. Now I said these are only the index, whatever the index values from 0, 1 to 26. So that is why these range from 0 to 24. But I want to know what are the actual values that are present in my cross validation set I consider. So these are the values. The values, if this is 0, that means the value in them is 1. So I'm considering 1 to 9 values as my testing, the remaining to be training, 10 to 17 to be my testing values, the remaining to be my training, On the similar hand, I have 18 to 25. Okay, fine, we have done all this. But what is actually happening over here? To do that, so to understand, to visualize what we're actually doing, let's try visualizing them. So before visualizing, let's try to first put these values in a proper ordered manner so that we can visualize this better. So I'm creating a function over here. What is the function's name? It is k4 size. And what are the arguments it's taking into consideration? It is considering kf. What is my kf over here? My kf is nothing but the k-fold validation, whatever. So if I, for example, if I put k5 5, k5 of 5, that means I want to visualize k5. k5 3, I want to visualize k5 3. So what is the next parameter? We have Rn. What is Rn? Rn is my entire range of values from 1 to 25. Next, what is this shift value over here? The shift value indicates that we want my training and testing to be shifted by a particular 0.1 amount so that we'll visualize it better. Next, I'm creating two duplicate data frames. One, I have the train duplicate data frame and I have a test. These are two different data frames I have into consideration. I'm keeping a value of I is equal to 1. What does this I signify? I nothing but tells us it is the k-fold, the number of folds that we are coming into consideration. Now, we are not doing anything new. Over here, as we use a function as np-take to iterate and use only the values and not the indexes, this is the same statement that we discussed before that we will be putting over here. For the train and test index in the kf.split, we will be taking the values over here and we would store these values in a column X. The column X consists of these values that are present. What are the values? The training values. That means these entire values I am nothing but storing in a column known as X. Then I am creating another column known as validation column or considered as val. What is this val? It is nothing but used for visualizing. As I said before, we would be moving the training values of -1 and we'll be moving the test values +1 just for visualization purpose and nothing else. The same thing, then we would append these values into a duplicate data frame that we have created before. The same procedure would be followed for the test data. I would store the test indices. That means what are the test indices? These are my test indices. This 1 to 9, 10 to 17, all those. Those will be my test indices. I'll be storing those test indices that are present in my test DF. And for testing data, I'm moving it +1. I'm appending it back to my original test data that I have. And what is this function returning to us? This function is returning the train and the test values. Now, we have created a function. Let's start inputting values into it. So, what I'm going to do is I'm going to try visualizing this K5 and K3. These are the two K4s that we created previously, isn't it? Let's try visualizing how these are present. So I have train 5, test 5. Why am I telling this? Because the function returns what? Train and test. So in the same order, I'm assigning variables to it, saying train 5 and test 5. I'm passing, what am I passing are the arguments over here? I have K5 and my entire set, that is Rn. Then I have train 3, test 3. My entire K-fold function, I have K3 and Rn. Now, I'm plotting this. What am I saying? I am saying that let my K5, that is this train 5 and test 5, this be in axis 0 and let this be in axis 1. I'm considering the x values to be the entire features, the y values to consider the values that we have shifted, like we have shifted +1 and -1 over here. That will be my val and my color. So I'm telling when my training be in blue color and let my testing be in red color. S is equal to 15 signifies that we have the size of each of the point to be 15. Then what is my data over here? If I'm training, then my data will be train. If I'm testing, my data will be test. And similarly, we do the same procedure for 5 and 3. What are my labels over here? I want my Y label to be K-fold and I'll explain it with the graph now. So this is the graph that we have obtained. What is this graph meaning? What are we coming to say? We can understand from this graph that there is a small difference over here that this is nothing but we can see the blue is nothing but my training and the red values are my testing. So that means that my blue value has moved a bit from the origin and this has this was the reason for us to introduce a new column known as val, where it did plus of 0.1 for training and minus of 0.1 for the testing. So by this, we're able to visualize how the testing is being moving in such a pattern. But what is happening up here? So let's try visualizing with this. So let's consider the first iteration over here. What is the first iteration? This is nothing but for a split of 3. So what is my testing data? I have 1 to 9. So let's dive over here. In my testing data, what did I consider first? I have values from 1 to 9. These are my test these are my testing values that are from 1 to 9. Sorry, up here. So we have from 1 to 9, we have my testing values. Then I have from 10 to 25 my second training values. On the similar hand, let's go back up here. What do we have? 1 to 19. 1 to 9 over here. 1 to 9 is nothing but my training values. So is that the same case over here? Yes. 1 to 9 is my training values. Then what is my testing? My testing is from 10 to 17. Let's see over here. 10 to 17 is my testing. The remaining values are training. So we see that we're keeping a stable test values, and whatever our remaining values are training. This nothing but helps us understand that even though we insert our values from 1 to 24, the model nothing but does not just run all the values by just doing a normal train split, but it divides them into equal parts in the parts that we want, whether it's threefold, fivefold, or whatever. When we see fivefold validations, we could see more clearer, where we have the initially, we're considering the training values to be 1 to 20, sorry, 0 to 20, and then we have the remaining values to be the testing. So keeping a standard test value, what are we doing? We are updating the training values, and the remaining values become our training values. Now, we can also see how many data points that we have into consideration. So for this, we're creating a function k-fold stats. We want to know what are the minimum values that are present in our train and test. We can have the minimum value, we can know the minimum occurrence, the maximum min and max length that are also present. So what is the minimum value that are present from this? It's 1. The maximum value, because we have 25 points, automatically we'll have maximum value as 25. What is the minimum occurrence? Minimum occurrence, we can see that the train 5 has a minimum occurrence of 4 and train 3 has a minimum occurrence of 2. Similarly, let's go to minimum length. 2016. Maximum length 2017. Max occurrence 4 and 2. That means we're giving a lot of priority on training. We're assigning a lot of values that are present for training. A huge amount of data is trained. Side by side, we are testing as well. It's not like the first 20 are training and the last 10 are testing. That is not the scenario we are doing over here. We are trying to do both of them simultaneously so that if it has unseen data, like we discussed before, it doesn't overfit and underfit, and we can move further. Now, this next we have is shuffled K4. In shuffled K4, the only difference that we have over here is whatever we discuss now is a normal K4. In normal K4, if you guys remember, we put shuffle is equal to false over here. Why did we put shuffle is equal to false? I want my training to be separate, my testing to be separate, and I do not want these to combine with each other. But I'm doing this for shuffle K4. Any doubts? Does anyone have any doubts?
Saraswati, you have any doubts? I think you can continue.
Okay, so moving forward with shuffled K4, the only difference that I'm going to do over here is I'm going to tell shuffle is equal to true. And for better visualization, we're going to have a random state as 42 for the fifth of for the K5 split, and for the K5 split we're going to create two of them, one with random state 42, one with random state 123. What is this random state? We just want to make sure that all the values that are present are in the same range and they do not change as such. So whatever we did before, the same thing is going to repeat. But let's just say we're keeping a shift of 0.25. We have a shift of before 0.1. Now we're having a shift of 0.25. We're going to proceed with the same thing that we did before. So what did we do before? We put for ever 0 as over here. We put axis 0 for the train 5, axis 1 for train 3, because we had for K5, K3. Now let's just deal with K5. We are dealing only with K5. But in K5, we have 2, 42 and 123 as the random state splits that we have into consideration. So what are we going to do? We're going to consider axis 0 as train for, so we're considering axis 0 for this. Then we're considering axis 1 for this. That is the same fundamentals that we're going to put over here. Now let's see how this moves forward. So as we said before, first, what did we have? We had training over here, then we have the testing. Training, the testing, again training. But this is not happening over here. First, we have the training. Intermediately, we're doing testing. We have training, testing, training, testing. We keep doing this so that, as Supraja mentioned before, the theory part of this, the main fundamentals that we are focusing up here is that we do not want our model to overfit or underfit when it sees new data. So when we do simultaneously training as well as testing, it helps us to nothing but prevent overfitting and underfitting as well as increase our model's accuracy. Now we have seen everything with the values of from 1 to 25. But how does this actually work? How do we see it on a real life data set? So to work it on a real life dataset, we'll be using Iris dataset. But before we dive deep into it, let's just summarize what are we going to do in this. So what are we going to do? We're going to split the entire dataset into K-folds. We're going to train it with K-folds. We're going to test it with the one fold, that is a K minus one fold. And then what are we going to do? We're going to compute the average performance. So this is our dataset. What is my dataset? I'm loading the iris dataset. It's a flower dataset. It consists of four main columns. The features of this are sepal length, sepal width, petal length, and petal width. And we have three different types of flowers over here. The flowers that we're going to, that is a target column that we're going to predict over here is the flowers. What are the flowers names? Sentosa, versicolor, virginica. How many samples do I have in each of them? I have 50 on each of them. What and how are the loops are nothing but iterating in this? First, I have I'm creating a data frame where I'm selling my data is nothing but my iris data. This is a data that is inbuilt that are present. So we're just loading it from the sklearn library that we discussed started. And my columns are my feature names. Now, what are my features? My features will be my last column that is over here present, the column that we want to predict. And my target name is nothing but these. So it's perfectly understood. What do we want? We want the first 5 samples. Now, what am I doing? Each of the target that are present, I'm saying these are the samples that are present and this is my target name. So now let's do the normal thing that we do. Let's create a logistic regression model and see how this nothing but works well. So to create a logistic regression model, as we initially over here, we had loaded the logistic regression models from sklearn.linear model. Similarly, we had loaded datasets from load iris. Anyone has any doubts? Okay. I should continue. So we are using a logistic regression model, and so what type of classification this is? We have 3 different types of classes. So it's a multi-class classification that we are dealing with. So we are using a multi-class classification. What is my X? My X will be all these features. All these features will be my X, except the target name. And what will be my Y? My Y will be just the target name that is present. And that is what we're doing. We're doing a normal 80-20 split that we generally do. Then we're fitting the model. We're predicting what is the accuracy on the train and accuracy on the test. We can see that the accuracy on training is 0.95, but the accuracy on test is 1. Usually in machine learning models, it is very rare that we get 1% accuracy. That means that our model is either underfitting or overfitting. That means that there is some problem happening over here because we cannot exactly accurately predict the model on the test data. So we feel that there's a lot of some accuracy. This is nothing but very high. So it's either overfitting or underfitting. And this is my training accuracy in the training data. Let's remember these values. That is 0.95 and 1. Now,
Yeah, Ritika. Yeah, 1 minute. So I want to ask a question over here. So the accuracy on train test is 0.95. So I want you, like anybody from the audience, like to tell me what is it overfitting or underfitting? Ritika didn't reveal the answer. What is this? Bonus marks, guys. Anybody can unmute and answer. The accuracy on training data set is 95. and on test it's 1%. So what is it? Overfitting or underfitting? Let us see if you've understood what I've told. Anybody? Chat box? Yes, correct. Proceed, Ritika. Good. Yes,
Yeah,
correct.
perfect. Yeah, it's
Correct.
overfitting. We see that the
Continue.
model is overfitting. So, as Supraja mentioned, we can move forward with the cross validation. But before we get into cross validation, let's see in a specific how these values are nothing but getting overfitted by using an ROC curve. Now, what is an ROC curve? An ROC curve is a graphical representation used for us to evaluate the performance of a binary classification model. We can use for binary as well as multi-class. Over here, we're using for multi-class. It shows the trade-off that is present between the true positive rates and the false positive rates. So for doing this, what do we have? We have X is the feature, Y are the targets. And I'm storing the true positive rates in an array and the AUC values, that is the curve values in an array. Then what am I doing? I am iterating towards the train and the test values. I'm using iLog as a function over here to nothing but get to know what are these values that are present. I'm using model regression model that is present, whatever we discussed above. We're predicting those values and we're seeing how these values are moving. We'll go with the curve. We'll go with the graph initially. So what is so in
Yeah,
this
Ritika.
graph,
Yeah, I will. Ritika, I'll cover ROC curve. Yeah, let us cover the theory and then understand what ROC. So you guys will understand what is ROC curve. Yep.
yeah, we'll see in detail how it is, but then I would just explain why it is overfitting as such for now. We would discuss about it further. So we can see that all of these values that are present exactly perform over here. This is the ideal line. The purple is the ideal line, and we see that all of them are exactly moving towards that corner. They want to reach that particular corner that is the exact values. Through this, we can see that these are nothing but overfitting over here. We would discuss in detail, but through this graph, we just know that because they all combine at one particular corner over here, these are nothing but overfitting. Next, in the same data, because we know that these are overfitting, that is why we have the concept of k-fold that comes into consideration. So how are we doing k-fold? To do k-fold as such, we are nothing but loading this iris dataset and we are manually doing the train and the test. What are we doing over here training? I'm considering whatever is the train index. What is my KF3 split? My KF3 split is nothing but my split of values for my k-fold that I have initialized, and I'm having the train index, and these are all my features that are present. Similarly, my test will consist only the features and the test index. My train, by train on the other hand, will contain the train index and all the values, but only my till my target value. I will not consider my target. The test will contain only the target. Now, when we see the accuracy for training these models, why is it that we're getting zero on the first four, second four, as well as the third four? Anyone wants to try figure this out? Why we're getting accuracy as zero when we do k-fold initially? Or
Boolean
anyone
mark.
wants to answer?
Give it a try, guys.
What was the main issue that we moved to k-fold? We could have normally done an 80-20 split, right? Why did we move to k-fold? Why are we getting an accuracy zero? Any one person who wants to volunteer and respond? I guess Supraja, we should start picking up names from the
Yeah, I
people who
think
are
we should do
present.
that. Guys, come on, give it
Yeah.
a try. Even if you're wrong, it's fine. It's all about learning. Come on, you can give it a try. Or Ritika will randomly pick somebody to answer. Okay, somebody has put class. Okay.
Okay. More
More,
answers?
more answers, guys. If you guys are interactive, then only we'll be more interested then. Anything you can. You can just prompt any answer. Whether it's right or not is a different thing. Only class imbalance, that's all. Only bonus marks for Shilpit then.
Let's give another chance for people.
Yeah. One more
Come
chance.
on.
5 marks. Nobody's ready. You continue with it.
Okay, yeah, so class imbalance is correct. We saw that we had the problem of overfitting. So, what is overfitting? What Supraja mentioned. We're training the values on, so let me take this with this model. So, first, what are we doing? I'm training on Virginica versicolor. I'm telling it to predict on Sentosa. If the model has not even been trained on Sentosa, then how will it predict Sentosa? That is the reason why we are getting our test accuracy as well as basically the test accuracy. After training, we're getting the test accuracy as 0 because we are training it on different values and we're testing it on different values. That is the reason why we got overfitting as well. The model was not able to predict what are the new values that are present. Next, let's just visualize this. For visualization, what are we using? We're using the target column that are present. What was our target column over here? If you guys remember, the target column consisted of, the target column was zeros and 0 for Sentosa. Virginica had 2 and 1 was for the other color, that is the versicolor. Moving down. Yeah, so these were the target columns that are present. Now I'm going to plot these values. The figure says nothing but the total size in which we want our figure to be visualized in. And I'm just scattering the plot with the target indexes and the target values with the color to be blue for the target value for the training values and the color to be red for the testing values. So we can see in my first fold what is happening. My first floor, the Virginica and versicolor are been trained. I'm telling to print on Sentosa. In the second fold, I am training it on Sentosa and Virginica. I'm telling her to predict on versicolor. And my third fold, what I'm doing, I am training it on Sentosa versicolor. I'm telling it to predict on Virginica. If the model has not even seen these values, how will it predict? How will it be able to nothing but say that the third flower is this? That is why we have that is why we moved with other K folds that come into picture. The other K fold is shuffle K fold. In shuffle K fold, what did we do? When we did with the normal data from 1 to 25, what did we say? Normal K fold meaning we have the shuffled equal to false. Let's come back over here. What did I say? We have my shuffled values equal to false. I have my shuffled values equal to false. Over 1 second. So I have my shuffled value equal to false if I'm doing normal K4. And why did we say this? We want a training to be separate and then we want a testing to be separate. Then we came to another, now we have moved forward with the shuffle K4. In shuffle K4, what are we doing? We're telling my shuffle value to be true. So whatever values you've done before, the same thing remains. It's literally the same data. Whatever code that we have written over here, we use the same code. But what are we doing? We're using the shuffle to be equal to true. We're giving a random state to it. So my X values are the features and my my training values are my features of the train index. My testing values are the test index of only the last column, that is my target, and the feature columns. Now we can see the test accuracy for the first fold is 98. For the second fold is 94 and 88. But what did we see over here? We saw it was 0, 0, 0. And over here it is 98, 94 and 88. Why has this happened? This is because in each of the training that is present, we can see from this image that if this is the entire training, I am consecutively doing testing as well. I am not telling it I am not training only on Virginica and versicolor and telling it to predict Sentosa. That is not what I'm doing. I am simultaneously training and testing in Virginica itself in such a manner like 70% is training, the next 30% is testing. These are random values that it has tested and trained on, but it gives us a better accuracy. From 0, we see how much drastic impact that this has caused. For each of the flower, for each of the Virginica, I'm doing train and test. Each of the samples of versicolor, I'm doing train and test, and Sentosa, I'm doing this. So because of this, we're able to get a higher accuracy. Now we can see the values that are being split in this. For versicolor, I have my train 1 and test 1 as 39 and 11. Then if my train is 39, my K42 I have 33 and my K43 I'm training with 28. Simultaneously, I'm testing it with 11, 17 and 22 side by side. It is not that I'm doing training first and then in the last I'm doing testing. That is not what we are doing. Simultaneously, since we are doing, the model will be able to learn better predict better as such. This is the same thing that we're doing for Virginica and Sentosa. Now let's see another thing that we have over here, that is stratify K-fold. In stratify K-fold, what are we doing over here? In stratify K-fold, we are saying that my shuffle is equal to true, as well as we are trying to put a random state of 123 over here, and we are seeing how these values are moving. Now in stratified K-fold, what are these values we can see? We can see that we have the same thing. What do you guys think would be the difference that is present between my shuffled K-fold and my stratified K-fold that is present over here? Do you guys see any difference from this and this? Anyone wants to give any answer? Anyone, guys? Anyone wants to volunteer and try figuring out what is the difference between these two? Okay. Because they have no response, I'll move forward. In the shuffle K-fold that we consider here, let's take an example. If we have a data set of 90% of class A and 10% of class B, some fours may end up with only class A. That may lead to poor model generalization. But when we move to stratify K-fold, what we are doing is, we can see over here the accuracy and we are double checking it. Each time we are checking what is nothing but happening over here. So if the data set, the same example, we have 90% of class A and 10% of class B, stratify K4 makes sure that each of the fold are almost in the same ratio. We can see that when we are double checking it, all of them could be on the same ratio. For of course, the first time when we're moving, we would get 1. But there's not a lot of difference present between the first and the second, 92 and 95. It's not that big. But then over here, we could see 98, 94, 88. 88 and 94, there's a lot of difference that is present between them. Whereas in stratify K4, that is not there. It makes sure that the proportion is nothing but constant throughout. Even though the graph, nothing but might look the same, but internally, this is what happens. Both of them are proportional with each other. Then let's see the values that are over here. The values over here are 33, 33, 34. And what am I testing it with, Virginica? 17, 17, 16. Let's just dive back here. What did we do over here? We're training it on 39, 33, 28. 11, 17, 22. Aren't these values all scattered? One is big, one is small, one is medium. These are just scattered and not in a proper manner or a proper order. Thereby, it will be hard for the model to nothing but learn when we progress further. So by using this equal split of data that is there, the model will be able to see when we have unbalanced data set, like how we are having this data set, as well as for different data, it's purely random when we talk about shuffle K4. But over here, there's a proportion that we are following so that it can learn better and test better. That is present. Then moving on with leave one out. When we see leave one out, as Supraja mentioned, it's a special case of K-fold validation, where each data point is used as a test case exactly once, while we have the remaining one data set that is present. What are we doing over here? Initially, we are going to now combine and see what is the difference that is present between a normal K-fold that we do, that is a shuffle K-fold, and the normal K-fold that we're going to do is the loop. We're going to plot both of them and see what are the differences. So what we're doing, the same, I'm telling axis 0 as my training, the axis 1 to be my train 123. So that means axis 0 for loop and axis 0 for my cross validation of 42. That is the thing. My x will consist of all the values. My val will consist of values that is +1 that is present for training and -1 that is for my testing that we had seen earlier. My color for blue for the training, color for red for the testing. The label I'm giving as train and test. In the similar manner, I'm putting my Y label, X label as K-fold features, my title as shuffle K-fold with random state 42. These are my things. Now let's come to this image. In my normal K-fold, shuffled K-fold that we're doing, we see that we are doing simultaneously. For each of the iterations, we're first testing, training, testing, training, testing, training. So this is we're doing it simultaneously. But what are we doing over here in features? If I have nothing but 10 features, I have over here 25. If I have 25 features over here, what am I testing it with? I'm testing it with only one of the value. So, what is the disadvantage in this? We have discussed before. Anyone wants to come up and say why we're not supposed to use leave one out? What are the disadvantages in this? Come on, guys, we just discussed. What is the difference that you can see between shuffle, k-fold, and leave one out? What is the
Yeah, I think I
disadvantage?
see this. Yeah, for large data sets, it's difficult to train. Model is familiar with testing data as well. I see two answers. One is basically we can't do for 1 lakh data points. Correct. Another disadvantage is high variance. Correct. We have
Yes,
answered
perfect.
this. Yes.
Perfect. So this is the thing. So we have that for each of the data points. If I have 0 to 25, the last only one data point from each of the iteration is what I am training and testing it. Now that we have learned different types of K4s that are present, we have K4, shuffle, stratified, leave one out. Now what is the best thing that I'm supposed to use? Usually what is the best recommendation for us to do is that if we have a bigger data set, a very large data set, we would usually go with a 5 to 10 k-fold validations and k-fold validation if it's a normal data set. If we have time series data set where we have to predict the housing range or we want to predict stocks, that means I want my data to remain the same. That means last 10 years of data should remain the same. The last next 5 years of data should remain constant. So in such a scenario, we will move forward with that. We want our data to remain the same. When we have for what? House pricing, stock price, or any kind of that, then we make sure that we use only a k-fold without shuffle. But whereas when we have normal data predictions that are present, we can use a shuffle k-fold with large amount of data. So this is done with cross-validation. Moving forward, Supraja will take forward.
Thank you, Ritika. Now, yeah, there is one component which I will be explaining, which is the ROC curve, which Ritika would have shown you. So I will start with that. Yeah. Is my screen visible, Ritika?
Yeah, it's visible.
Yeah. Okay. So now there's we are going to discuss about this ROC curve. So this is why do we need this curve? Anybody? Any idea? Okay, I'll start. So I'll give you a real world example. So we have a spam filter. Suppose we have a spam filter. Now it what does spam filter predict? It predicts whether an email is spam or not spam. That's what it does. Right? So now what happens is sometimes the spam filter correctly marks spam. That is fine. But sometimes it mistakenly marks an important mail as a spam. Okay, so now I told two things over here. Sometimes it correctly marks spam. So when I say it correctly marks it as a spam, it's called true positive. So I think you all know what is a confusion matrix, right? I think last class we had done that. Yep, we had done. Okay, 1 minute. We had done the confusion matrix, right? So this confusion matrix, which has this is the true positive, this is the false positive. So I'm talking about these two components of the confusion matrix. So let me go to the slide. Yeah. So as I was talking about the true positive. So in the confusion matrix, it is this segment. This is a true positive, and this is the false positive rate. So now I have when it correctly marks the spam email as spam, it's called true positive. When it mistakenly marks an important mail as spam, it's called false positive. False false positive. So now this curve which you see, which is the receiver operating characteristic curve, this ROC curve will help us measure how well the classifier is balancing between detecting a spam and avoiding mistake. It was a real life example that it doesn't have anything to do with filter. I just explained through an example. So you guys have a spam filter. The spam filter will predict whether a mail is a spam mail or a non-spam. So when it correctly predicts the spam mail as spam, it's called true positive. When it incorrectly marks an important mail as spam, it's called false positive. This curve, which we are going to discuss right now, tells us how classifier is balancing between the true positive rate and the false positive rate. Just an introduction. Now we all see a ROC curve here. So here we have the in the x-axis we have the false positive rate. This basically tells us how often the model will incorrectly predict a negative case as positive. That is the false positives role. I repeat, it will tell us how often the model incorrectly predicts a negative case as positive. So we need a lower value. So for false positive rate, lower value we need. We need lower value means a few mistakes will be detected. If it's a higher value, then there will be a lot of mistakes. So for FPR we need a lower value, lower value. Next, let's come to the y-axis, this part over here, which is the true positive rate. This basically tells us how many actual positive. What is actual positive? That is the spam mails which I don't. It had correctly identified, right? So this TPR tells us how many actual positives are correctly identified. So here we need a higher value. A higher value means a better detection. So this was the thing. Now you see multiple lines in the graph. We will decode them one by one. So first let me start with the purple line which you see over here. The purple line. This is the purple line, guys. The purple line. And the so this purple line is a perfect classifier. It's written over here. It's a perfect classifier which has a TPR of 1. It has a true positive rate of 1 and a false positive rate of 0, meaning it has made no mistakes. It follows a sharp L curve, which you guys can see. Okay, this is the L, ulta, reverse L, meaning no mistakes. This is an ideal. This is the ideal case, but it is often unrealistic. Do you think everything in life is ideal? No, we have a lot of these things, right? So this is ideal, but often it is unrealistic case. We always wouldn't get a perfect classified. So we are done with the purple line. No doubts about purple line, right? Anybody? Please stop me if you have any doubts. Next, now let's go to this dashed line, red color line, which you see, the random classifier. This random classifier basically, basically it's what it does is this line represents where a model basically guesses randomly. It does guessing randomly. So that is why it follows a diagonal from all the way from 0 0 from this coordinate 0 0 all the way till 1 1. That means the classifier has no. Basically, this line tells us that the model has no ability to distinguish between classes. Okay, so if your model performs around this line, it is no better than flipping a coin, guys. I'm sorry. If your model performs like this red dashed line, it is no better than flipping a coin. Okay, so I hope purple line is clear, red dashed line is clear. Okay, purple line was a perfect classifier, which is basically the ideal one, but the red dashed line was basically a classifier which had no real ability to distinguish. Now let's come to the typical classifiers. So um, let me erase all this so that it okay. Allow space to write. Yes. Okay. Let me start. Let me take orange color. Yeah. Now, now you see that your typical classifiers are which color? They are in blue color, orange color. Yeah, this is orange color, guys. Orange. Then we have green. Okay, these are basically a typical classifier. These are basically these three which you see. These are the real world models. These are the predictions or they made by the real world models. So these are closer. If you see, these are closer to the perfect classifier. Okay, so the blue curve. So here the blue curve is better than the orange curve. The orange curve is better than the green curve. Do you guys agree with me? The blue curve is better than the orange curve. The orange curve is better than the green curve. Okay, the blue curve is better than the orange curve. Orange curve is better than the green curve. Yeah. Now let me explain when I'm talking about better. What do I mean by better? So better means the higher the curve, the more it bends. You see, the more it bends towards the top left, better is the model. That is why this line over here, you see over here, the arrow which I have put, that basically tells us the black arrow labeled better shows that the higher the curve, the stronger is the classifier. A better model correctly identifies the positives while making very few mistakes. Okay, this is the whole curve. Okay, so if I have to just sum up the whole thing, the model area under the curve. So area under the curve is AUC. That's the area under the curve is the better the model. Okay, the more area under the curve, better is the model. Better is the model. More area under the curve, better is the model. So if an AUC area under the curve is close to 1, it is excellent. But if it is 0.5, it is no better than random guessing, right? That is it. So this is about the whole explanation of ROC curve. Ritika will then show you the explanation. Before that, now let me tell you guys more cases about the curve. Now, how does a model decide? Now, here this graph tells us how a model decides if a person is infected or not. How will you? How does a model decide if a person is infected or not? And how do we measure if our model is, if this particular model is good or not? Now if you look at this graph, the left graph over here, this tells us it tests the class they test the basically the classified people, it classifies people as uninfected or infected based on the threshold. So this x axis has the threshold, which basically represents different cutoff points for deciding the positive. The positive is for those who are infected, and negative for those who are uninfected. Okay, so this graph, the left graph, basically what it shows how a test classifies people as infected and uninfected. X-axis represents the different cutoff points for it's the threshold, which tells us the different cutoff points for deciding positive or negative. Now you see the red curve. This is the red curve. This is the blue curve. Now the red curve is the true negative. That is, it represents the score. This is the healthy people, the score of the healthy people. The blue curve, which is the true positive, represents the score of infected people. This is the uninfected people, which are the healthy people. These are the infected people. Now the vertical line which you see, this is the vertical line, the 0.5 you see. Now here the vertical line 0.5 is chosen as this threshold. For this graph, 0.5 is chosen as threshold. Now if the score is if it is less than 0.5, then what it suggests? It is the negative scenario. It is the negative case. That means true negative, people are healthy. Healthy or nothing but uninfected. But if our threshold score is more than 0.5, that means it is the positive case, people are infected. So the better the separation, more accurate will be our test. This is it about this graph. Hope no doubts. Hope we have no doubts over here. Next, now come to this graph, the right hand side graph. Now this is basically, again, it tells us about the ROC curve, which I just explained in the previous slide. It tells us how well the distinguish happens between the positive cases and the negative cases. Okay, positive cases and the negative cases. Now, x-axis FPR, y-axis TPR. You guys are pretty comfortable with it right now. Now, basically, the x-axis will tell us how many healthy people were incorrectly labeled as infected. FPR, the x-axis over here, basically tells us how many healthy people, HP is healthy people, were incorrectly labeled as infected. While our TPR is basically tells us how many infected, IF is the infected people, were correctly identified. That is the TPR. TPR, FPR clear? Now, a perfect test would identify the red line which you see now, which is perpendicular. This basically would identify all positive correctly and have no false positive. So this means the AUC is 1. Sorry, the AUC is 1, meaning the red border touches the top left corner which you see over here. AUC 1 means the test is 100% accurate. That means it never makes a mistake. This is about this. Now let us look another case. Here, again, we're imagining a test that predicts if a person is infected or uninfected. Now, the red curve is basically the healthy people. The blue curve is basically the infected people. Now, what can go? Now, the middle line is what is the threshold, which is 0 point, the cutoff point, where this is the 0.5 basically is the cutoff point where the model decides. It'll decide. Now, what can go wrong in here? What can go wrong? What can go wrong? Here we have two more terms, FN and FP. So FP is what? FP is, let me write over here. FP is what? FP is, test says someone is infected. Someone is infected, but in reality, they are actually healthy. False positive means the test, whatever test had they had done, told they're infected, but they're actually healthy. That is FP. What is FN? FN is, the test says someone is healthy, but they're actually infected. The test gave a wrong result saying it is healthy, but in reality they are infected. So I hope FP and FN is clear. FP was what? The person was, the test said that the person was infected, but in reality the person was healthy. FN was what? FN was, the test says the person was healthy, but in reality the person, he or she, was infected. Now what we want to do, we want to reduce mistakes. We want to, our goal is to reduce mistake. Our model, we want to prevent the model from making mistakes, reduce mistake, and pick the best threshold between FN and FP. So if you see the right hand side, this is the performance graph. This is what you call, this is the ROC curve, which tells us about the performance. Now what happens over here? X-axis FPR, y-axis TPR. False positives, next true positive. This is the wrong predictions, this is the correct predictions. Here we get an AUC of 0.8. This means the model is 80% good at distinguishing 80% good at distinguishing infected versus uninfected. Okay, I hope it's clear. So what our goal was here, we had to find out what we wanted to reduce the mistake, and we wanted to pick the best threshold to balance between FN and FP. So we wanted to see how good the model is. So when we see the performance graph, which is the ROC curve, we could see that AUC was 0.8, means the model is 80% good at distinguishing between the infected versus uninfected. And what is the perfect model, guys? Perfect model is AUC is 1, means it's a perfect model, 100%. That means it can never make a mistake. So here the left graph, what it showed us how the test decides if someone is sick or healthy, and the right graph showed us how the test works. Okay, how the test works. And AUC 0.8 means the test is 80% accuracy. Now another graph, and the performance graph is over here. This graph again basically tells us about the whether the person is infected or uninfected. So we have the threshold, and then y-axis is the probability distribution. Now we have again the threshold. We have that between line set to 0.5. Now y-axis basically tells us how the model assigns the probability to the different cases. Now what we need to observe over here is we have all four terms here. We have TN, we have TP, FP, and FN. Okay, this is FP, and then we have FN. We have all whatever the terminologies you can see. You know all these terms, right? What is TN? TN is the model correctly identified the person is not infected. TN is true negative, where the person correctly identified, where the model correctly identifies the person is not infected. TP is the model correctly identifies the person is infected. Person is infected. Here not infected, person is infected. FN is what? FN is basically the model incorrectly says that model is saying what? Model is saying not infected, but they're actually infected in reality. So false negative is what? Model is saying not infected, but in reality they are infected. Here what is false positive? False positive is what? The model incorrectly says someone is infected. It is wrong. Incorrectly says that they are infected while they're actually not infected. So here our main goal of a good model. What is the main goal of a good model is to maximize the true positive and true negative. Our main now what the four slides, the four graphs which I try to portray, the whole goal what I'm trying to say is it is to maximize the TP and TN, and minimize FN and FP by choosing a good threshold. The whole factor or whole funda rise over here, where I have to choose a good threshold. Okay. And ROC, you can see over here, this I already told about the red dashed line which we could see. Here it is doing 0.5. Means it's randomly guessing. Like I said, no, it's like just like flipping a coin. Random, it's no better than flipping a coin. Because AUC tells us how good the model is at separating the class. When it is 0.5, means like it's just that random guessing is happening. So here you can see the left graph shows how the model makes decision. Right graph basically told us the model is complete. This model is completely useless because it's just guessing. A good model should have an AUC greater than 0.5. Okay. Yes. Now let us look at one more graph, and then yeah, I will not make you guys bored. One more graph, and then we'll discuss another topic. Now here, what do you see here? We see here x-axis, y-axis. We're clear again. X-axis threshold, y-axis probability distribution, TP, TN. Okay. Now what I wanted to discuss over here. So TP, TN clear, and the threshold if it's basically used for classifying individuals as positive, P positive or negative. So if this particular threshold, if it's poorly chosen, it will affect the performance graph. That is what I'm trying to imply. If it's poorly chosen or the okay, then it will misclassify. That is the main point I would try to draw your attention to. So if our threshold is not set properly or not properly chosen, it will misclassify many cases. So if you see the ARU's performance graph over here, here the AUC is 0.2, which is extremely low, extremely low. This model is worse than the previous graph, which was 0, AUC 0.5. This model only has 20% chance of correctly distinguishing between infected and uninfected. Right? It's worse than the 0.5, worse than flipping a coin. Right? So this is the inference I would like to make this class because this graph is extremely bad. What I'm trying to imply again, I'm just recuperating the same thing, which is AUC close to 1 is the best classifier, is the good. But an AUC close to 0 suggests that it is making a critical mistake. Okay, so typically you won't see this unless you guys won't do this mistake, I hope, because unless you make a blatant mistake, I'm assuming nobody will get an AUC this thing AUC equal to 0.2, right? Now I will discuss about the final takeaway. I want to tell what you guys this curve. If you want to see the final takeaway is, I already told the model is terrible with AUC 0.2 because 0.5 only I'm telling it's worse. 0.2 is much worse than that. Like unless somebody makes a blatant mistake for this, nobody will get a AUC curve like this. Okay. Next, the final takeaway I want to take you this is the real life ROC curve. You can see FPR, TPR, again the same thing I'm repeatedly saying. So we have the now just the last ROC curve so that you guys have a proper understanding of what this is. So if you see here, there is something called optimal threshold and non-optimal threshold. I want to discuss and put some light on that. So what is optimal threshold? If you see the optimal threshold, this left hand side, optimal threshold. So this is the point closest to 0, 1 on the graph if you see, which means it has a high TPR. That is many true positives are captured and very low FPR. Very few false positive. Okay. The inference of optimal threshold is a high TPR, low FPR. So the accuracy is what 0.84. So the accuracy of 0.84 means what is it? It is considered optimal. This is optimal because it balances between both FPR and TPR. That's all I want to make an inference from this. Well, what is this non-optimal threshold? Here, this has, you will say, what are you saying? You had accuracy 0.84 and you claim that good. Here, accuracy is 0.92. Wait, guys, I will explain. What is 0.92? 0.92 means it has an high accuracy, but it is not balanced because this point has high accuracy, I agree. But this is very farther from the top left corner. Here, what is an ideal ROC curve? Like this, right? But here only I'm getting the accuracy, this thing. So this suggests that while accuracy is high, model is favoring only one class over the other. It is favoring only one class over the other. So here it is what is happening. What I can infer from this it is leading to more false positives or FN or false negatives. That is what I can infer from this. I agree, the high accuracy is 0.92, but what? But just accuracy is not a metric. What is happening is it is so far from the top left. I told you that here you see this is the ideal ROC curve, right? It has high accuracy, but it's farther from the top left corner. Accuracy might be high, but model is either favoring one class over the other. So it is. I told you what our goal is to maximize what our goal was to maximize TPN TN and minimize FP or FN. But here what our model is favoring or leading to more false positive or this thing. That is what I want to infer from this. AUC 0.84, it's good, it's quite high. So what does this mean? So it lies between 0 to 1. So now let's make a final inference. 0.5 is random guessing. 1 is what? Perfect classifier. Right? 0.8745. Model has what? Model has good discriminative power. That is what I can infer from this. It has good discriminator power. Okay. So let me conclude with ROC. What is ROC? ROC, I already told you, it is basically a graph between the TPR and FPR. Okay. It helps us choose the best threshold. We have to choose the best threshold for classification based on the balance between the TPR and the FPR. Okay. And the point closest to the top left, if you see, is usually the best trade-off. Okay, the point usually top left corner is the best trade-off between TPR and FPR. High accuracy always does not imply the best model. Just now you guys saw that. You guys don't immediately make assumptions that 0.92. No, high accuracy does not always mean the best model. We must consider the FN and FP case, FP also. Okay, this is what I would like to say. Got any questions, guys, about this thing ROC? Anybody? Shall we go to the next important topic of today's session? Okay, then I'll go to the next session. This is a very interesting thing. Yeah. Now I'm going to discuss about unsupervised learning. But before that, you guys might have a question. Before unsupervised learning, we learned about supervised. Now, won't supervised suffice? Why are we going to unsupervised? Anybody has a anybody can anybody answer this question? It's a simple question. Why are we moving from supervised to unsupervised? I know that machine learning has different types. Don't tell me that's the reason. We could have just been sufficed with supervised. Why are we going to unsupervised? Let me
Suprita,
give.
before we move forward, there's a question in the chat box. The question is, what is meant by threshold over here?
Yes. Okay. Good question. So threshold is basically the value. Yes. So where are we? Yeah. Is the screen visible? Yeah. This is the threshold. This is the value which we have to see. This threshold which we have over here, we should make sure we have to adjust this threshold properly so that we maximize the rate between TPR and FPR. If we set this threshold, if the threshold is below 0.5, then we can identify whether the person is infected or not infected, right? So what this says is basically, if we do not set the right threshold, then our model will perform very poorly. Threshold is basically just it's a thing which tells us about how well our model will be predicting. Okay, would that suffice or more explanation? If the 0.5, if our score is less than 0.5, then it is a TN case. That means we'll get patients who are uninfected. If the threshold is set beyond 0.5, then we'll get the case where the patient is infected. That is what the threshold is saying. So better the separation, more accurate will be our test. That's all. Threshold basically tells us the different cutoff points for deciding whether the person is infected or uninfected. That's all. This point is very crucial. This threshold is very important to decide whether the person is infected or infected. So this has to be set properly. Is it clear? Any more explanation or any more examples to be given? Ritika?
No, that was the only question. You can
Okay,
proceed.
yes. Thank you.
Supraja,
Yeah,
why don't we take a 5 minute break for everyone to just go
sure,
through
sure,
what
sure.
we have done and
Yeah, sure. Yeah.
So we'll come back to it in 5 minutes. All of you, please be in the meeting. Don't leave it. You can come back in 5 minutes. Hello.
Yeah, Abhinav.
So I hope everyone is back from the break and let's resume the session. So Prasad, you can continue.
Okay. Yeah. I hope my screen is visible, guys. Okay. Now, we had learned supervised learning last week. Sir had covered supervised learning. Now, why the transition from supervised to unsupervised? Wouldn't it suffice just to do supervised machine learning? Why unsupervised learning? Anybody? Okay. So I will be covering all those points. Why are we transitioning from supervised to unsupervised? So in supervised, if you had observed, there was labeled data. That is, last week I had taken example of placement data set. I had given all the features, and the target column was whether the student was placed or not placed. So this label was present. Or if I have a bunch of features for fruits, apple, banana, then we have grapes. So if I had using the features, if I had the target column, it said that using these features, it is apple, banana, and so on, or label data. So this label data, if it's in supervised learning, this label data is present. But in real world cases, we only have raw data, right? We only have raw data. So labeling is costly. Why costly? Because a human or manual labor is required for somebody to sit and do. It is time consuming. And sometimes it is impossible because let's take a medical scenario, that is diagnosis of a rare disease. Doctors can't manually sit and label millions of cases. It is practically impossible. That is one thing. So first thing is label data is expensive and limited. Next, uh, let me clear the pen markings. Yeah. So the next is discovering hidden patterns. So in SL, supervised learning, it was limited to the known categories because I had already given whatever the thing features are. Okay, and basically it will not recognize or identify any particular patterns. Suppose let me take an example. Let me take marketing an example. In marketing, we may not know all the customer types. As far as me as a custom, as if I'm in a marketing department, I'm assigned, I would know just there are two types of customers. One who's angry, one who's jovial. That's all I know. But there are different types of customers. So here we look clustering to identify the new segments of patterns. Next is basically if we have high dimensional data. Unless your computer is a supercomputer, it cannot process everything, right? So you can't in supervised learning we just can't handle with high dimension. Supervised learning with SL will struggle. While I'm using unsupervised learning, we can do PCA. We can reduce the dimensionality and we can find different patterns. Right. Next is fourth. Let me give you one more point. Why we're transitioning from supervised to unsupervised. Now we have to detect anomalies. You guys understand what anomalies, right? Any kind of rare events occurring, like suppose we are a bank, like some fraudulent cases happening, cyber threats. Okay, so a bank will detect a fraudulent transaction because it doesn't fit the normal. If it doesn't fit the normal spending range, so unsupervised learning will come in favor. But supervised learning, no, it can't identify trends and patterns, right? So unsupervised learning will basically pre-train DL models. I know you guys don't know what DL models is, neural networks, but then just know that it will help in pre-training deep learning models. Using that, you can improve the accuracy. Like, let me take an example. So let's take self-supervised learning in AI. What is ChatGPT, guys? ChatGPT is self-supervised learning. So I give it a large amount of unlabeled data text before fine-tuning. Right? ChatGPT doesn't. It is not like it already had all those answers which I had to ask for. No, it is learning. So this is why we are transitioning from supervised to unsupervised. Now let me formally define what an unsupervised learning is. So an unsupervised learning, it's basically NML, where the model learns from patterns and structures from unlabeled data, meaning there is basically no predefined categories. There is no human intervention. In unsupervised learning, we'll find patterns, similarities, and grouping in the data. And so commonly used task, basically it is used for tasks like clustering. Now, let me say you are working as a clerk in a firm. You have a lot of documents to be put into bunch. You have to cluster them. Clustering will help you. Next, you have a high dimensional data. You can do dimensionality reduction using unsupervised learning methods. So examples of unsupervised learning is clustering. Next, today in this main class, we'll be focusing about clustering. Next is anomaly detection. Anomaly detection, that bank frauds, the threats. Next is basically dimensionality reduction. So in this today's class, we are going to focus on clustering, basically grouping customers based on purchasing behavior, or I'm trying to find out the customer types. Okay, all those types. So what is clustering? Let me give you guys a visual animation or something. So what do we have? Different types of flowers here. We have sunflowers, we have daisies, tulips. Now I can how do you think I can cluster these? I can cluster these on many types. So basically, I can cluster them based on color. I can cluster them based on their, the round petal shape or whatever that is. So if you see, first thing I've clustered them based on color. Yeah, purple. So I cluster them. Next, yellow flowers into one cluster. Next, I cluster them based on round petals and tall vertical petals. So this is exactly what clustering is. So we have tulips, sunflowers, and daisies. That is another classification. These both are tulips. So I just had these four flowers, but I clustered them into three different ways, right? I clustered them based on color. I clustered them based on their features. Next is basically to their domain. So now I think you guys would have understood what cluster is. A cluster is basically a collection of data objects. And now we are going to do cluster analysis. So in clustering, we need to see a method called k-means clustering. How does k-means clustering? I will, any doubts in this question, please ask me immediately after I finish so that we can clarify it at the earliest. So in k-means clustering, what we do? So we partition an object into k non-empty subsets. Then what we do is we basically compute the seed points. Seed points is basically we calculate the mean. Okay. Next, we assign each object to the objects to the cluster with the nearest seed point. Then again, we iterate back to the step 2 when the assignment does not change. So let's take an example. So here I have these randomly initial data set. I have to arbitrarily partition into k groups. The k is equal to, that is 2. I have to partition into 2 groups. So here basically I randomly initialize the clusters. Then there is this thing. Then we update. Now then I calculate the centroid. Then when I calculate the centroid, you can see over here they'll be assigned. They'll be reassigned to their particular clusters, and then we will calculate the centroid and check whether they are belonging to that particular cluster. So we'll update the centroid and then we'll check. So we'll be doing partitioning these into k non-empty subsets. After we'll repeat the process of computing the centroid until they do not change, until each object is assigned to a particular cluster. We'll make sure that the convergence criteria, we make sure that we will not they are particularly present in that particular cluster only. They are not, their mean point or their seed point is not changing. So I will take an example and explain it. This is a very good example. So I have these data points: 2, 5, 7, 8, 13, 16, 18, 28, 30. I randomly assign one of the 2 to cluster 1, 13 to cluster 2, 30 to cluster 3. Now what happens? Now where should I put 5? 5 is closer to 2 or 13. If 5 is closer to C1. So I put it in the cluster 1. What about 7? 7 is closer to 5 or 7. What is 7 minus 2? Is 5. 13 minus 7? We put 5. Now I have to check 7. 7 minus 2 is 5. Next is 7 plus 6 is 13. So I think 5. I'll put it in. I put 7 also in cluster 2. Next 8. 2 and 8 difference is 6. But 13 and 8 is 5. So I'll put 8 in cluster 2. Next 16. 16 is closer to 13. So 13. Next is 18. 18 is closer to 13 is already in cluster 2. 16 I placed it in cluster 2. 18 is closer to 13 or 30. It's closer to cluster 2. So I did it. Next C3. C3 is 28 is closer to 13 or 30. It's obviously closer to 30. So initially I've done this. Now what we should do? Now we should basically calculate the mean point. How will you calculate the mean point? Basically 2 plus 5, 7. 7 plus 7, 14. 14 divided by 4 is 4.6. Now what is the next? I calculate the mean of this. 13 plus 8 is 21. 21 plus 16 is 37. 37 plus 18 is 55 divided by 4. Okay, you calculate that and we will get the this thing. Next, we have 28 plus 30. 28 plus 30 is 58. 58 divided by 2 is 29. So, I've calculated the mean for everything. Now, let us check, guys, whether these belongs to cluster 1 or cluster 2 or cluster 3. We will check whether these points have been assigned in the correct cluster or not. So, we'll check 2. 2 is closer to mean point 4.6 than 13.5. So, 2 belongs to cluster 1. Anyways, 2 was I assigned it initially to cluster 1, so it won't change. Let us check for 5. 5 is closer to 4.6 or 13.5. Obviously 4.6. So 5 will be in this range. Next, let's see 7. 7 is closer to the mean 4.6 or 13.5. Obviously it's closer to this only. Next, let's check for 8. Now 8 was belonging in the first step. 8 was belonging to cluster 2. Now we'll check 8 minus 4.6 is what? We'll check this distance and we'll check its distance with this. Obviously 8, the distance from the first centroid is closer. So 8 is now put into the first cluster. You guys see the difference? Next. Now let's check for the next point. 13. 13 is already belong to cluster 2. No need to check. 16. Obviously 16 is closer to 13.5. Hence will remain to this rather than 4.6. 18. 18 is obviously closer to this. Hence it will remain in the same cluster. Now let's come to 28 and 30. 28 and 30. It is obviously belonging, mean is 29 and it is belonging to the same distance rather than 13.5. So we have to repeat this problem until they lie in the, so until we should make sure that cluster 1 has only 2, 5, 7, 8. You have to again check, you have to compute the C point and check whether these points belonging to this. 13, 13 can't belong to 16, 16 will obviously be, so it has reached the convergence criteria. So we can say that in cluster 1, we have 2, 5, 7, 8. Then in cluster 2, we had 13, 16, 18. This is not changing. It has converged. C3, because why is it converged? Because I can again I'm checking the mean point. Whether 5 belongs to this, 7 belongs to this, 8. Can 13 belong to this? No, 13 was initially assigned to cluster 2 only. Next, we're checking if, for C3. Can 28 belong to 15.6? No. It can only it will belong to this because it's closer to this centroid point. C3 contains 28. Guys, any doubt in this? I hope this was very simple. Any doubts in this? I can explain again. Any doubts in this? Should I repeat? Hmm? Okay, I'll proceed. Now let's take an example. Might be this, you might be doing this numerical in your class again in future. So we'll just make you trained over here beforehand. So now what I'm doing is basically here our k is equal to 2. Okay, k is equal to 2. We have chosen the number of it's given in the question that k equal to use k equal to 2. Okay, that means we want to divide the cluster into whether C1 or C2. That is our ultimate goal. Okay, so what is my first step? My first step is randomly selecting initial centroid. So randomly I will select the individual. Randomly I will select this and let me take this. Okay, I will randomly pick 2 points from our data set. We have totally 7 data points. I will randomly pick 2 points from our data set as the initial centroid. So what is our initial centroid? M1 becomes what? 1.0. Okay, let me just clear my annotations. So let me use highlighter. Yeah. So I had taken this, right? I had initially taken this and then let us take this. Okay, so and I've randomly selected the initial centroid. So what is the initial centroid? Which is nothing but M1. What is M1? M1 is 1.0, 1.0. This is the individual one. And M2 is basically 5.0 and 7.0. Okay. Two centroids we have chosen, M1 and M2. Okay. 7 data points, each with 2 variables. Okay. Clear? Now I'm grouping the centroids. So the group 1 starts with the individual 1, where my mean vector is what? 1.0, 1.0 and 1.0, and group 2 starts with individual 4. Now I'll basically start grouping like you guys understand, right? What happened here? Initially I had initially assigned randomly 2 to cluster 1, 13 in cluster 2 and 30. So that is what I'm doing over here. Nothing rocket science over it. Just I've initialized that. Now next what I'm doing is, so this is what I've done, 1 and 4. So M1 is 1.0, M2 is 5.0. Now what is the next step is basically, now I will calculate this thing. So what I'm supposed to do is basically I will calculate the distance now. So I have to assign points to the nearest centroid. What I will do? So first I will do the math over here. So M1 was what? M1 is this one and M2 is this thing. So now what I have to do is I will check whether these clusters belong to which point. Okay, so I will check that. So I will do the Euclidean distance formula. You guys know the Euclidean distance, right? Our m1 m2 is this m1 m2 is this thing. I will calculate the Euclidean distance with the other points. Like I will do 1 minus 1 minus under root of 1 minus 1.5 the whole square plus 1 minus 2 the whole square. So I'll calculate that. Then I will check for the next point. I will check with this respect to this individual. I will check 5 minus 1.5 the whole square plus 7 minus 2 the whole square. I will compute the distance. Okay. When I compute the distance, I will get the value. I'll get one particular x value or y value over here. After that, what I will do? I will check. I will assign each of them to a particular cluster. So when I calculated that, so I'm getting two. So we calculated that the mean this thing for this point which I calculated. So we got that the centroid was 1.12 and this. Okay, yeah, here it is, guys. The calculation which I did in the previous page is over here. What I did one my yeah, the table you can see here. What I did 1 minus 1.5. What are they doing here? 1 minus 1.5. 1 minus 1.5. 1 minus these 2 points. Can you see these 2 points? Yeah. So I calculated the Euclid. This is the Euclidean distance. Okay, or the distance formula which you guys had used, right? So that is the formula. So after that, I got these 2 points. So what I did after calculating this, then I'm trying to check whether it belongs to which cluster. So now this thing initially I assumed that this is this this one belonged to the first cluster. So in cluster one, I already had one element over here, individual one. Next, which is the least among this? Obviously this thing. So two also belongs to the cluster one. Next, come to the third point. Third point again, if you compute the distance. Did you guys understand how did I compute the distance? I initially had 1.0 and 1.0 as my mean, right? And then another value was 5 and 7, I'm assuming. So what I'm doing with each point, I'm computing the distance. Like in my table, I had 7 data points. So with each value, I'm computing 1 minus that particular value under root of 1 minus that particular value whole square plus 1 minus that particular value minus whole square. Then this was the you have to come. We had two clusters, right? Then I have to check with this also. 5 minus that particular point the whole square under root of 5 minus that particular point the whole square plus 7 minus that particular point the whole square. Like that you compute and you calculate this distance. Now we are basically going to put them into clusters, which I had done in the blue color boxes ka example. So here 1.12 we got. So basically it belongs to the first cluster. 3.61, 3.61. So basically here I'll put them in the third cluster for now. Okay. Later again we'll see when we're computing the C points again, it might change. We'll see. Fourth one is basically is in the cluster 2. So fourth one is in the cluster 2. 5, 6, 7 are in the cluster 2 because their distances they're shorter towards the center. Their C points are closer to the second cluster. That is why they are in that cluster. So you can see that in cluster 1 we have 1, 2, 3, and in cluster 2 we have 4, 5, 6, 7. We did nothing fancy. What we did is initially we randomly we assumed two these things to be our centroids. After doing assuming them to be the centroids, we had recalculated the distance between them to see Euclidean distance we had taken. Then we computed the distance. After computing the distance, we had the table next table page table contained the distance from distance to centroid 1, and the another column contained distance to the centroid 2. So whatever distance it gave over here, we saw that which is the minimal distance, we assigned it to that particular cluster. That is all. Okay. Based on that, we got cluster 1 as this 1, 2, 3, cluster 2. Now the step is not over here because there's an ambiguity over here whether to put this in. I assigned it to my cluster 1, but let us check. So now what you have to do, you have to update the centroids. We have to update the centroids. So how do we update a centroid? Basically, what I would do, I'll basically take the cluster 1 contains what? Cluster 1 had contained 1, 2, 3, right? It had contained these 3 points. So let me take those 3 points. What are those 3 points? 1, 1, 1.5, 2, 3, 4. I'm taking these 3 points, guys. Okay? Oh my God. Sorry. Yeah, what I'm doing is I am taking these 3 points. So what I'm doing is I am taking 1, 1, next is 1.5, 2, 3, 4. What I'm going to do is I'm going to calculate the new centroid for cluster 1. So what I'll do 1, plus 1.5 plus 3 divided by 3, comma 1 plus 2 plus 4 divided by 3. I do this. 1 plus 1.5 is 4.5. 4.5 plus 3 is 7.5. 7.5 divided by 3 is 1.1.83. 1 plus 2 plus 4 is 3. 3 plus 4 is 7. 7 by 3 I get. 7 by 3 is nothing but 2.33. Okay. So now what is my this thing? 1.83 comma 2.33. Okay. So this is the new centroid. New centroid for cluster 1. Okay. Now I have to do the same thing for cluster 2. Cluster 2 had what odd elements? 4, 5, 6, 7. Okay. What I will do? I will do the same thing. So I will do 5 plus 3.5 is 8.5. 8.5 plus 4.5 plus 3.5 divided by how many points? I divided by 4 points. So 5 plus 3 is 8.5. 8.5 plus 4.5 is 13. 16.5. So 16.5 divided by 4 I will do, and then I will get 4 4 is 4.12, and then I will do same thing. 7 plus 5 is 12. 12 plus 5, I'm doing this addition. 7 plus 5 is 12. 12 plus 5 is 17. 17 plus 4 is 21.5. 21.5 divided by 4. Okay, which is nothing but 4 5 is 5.38. Okay, so for centroid 2 I got the new for cluster 2 I got the new centroid as 4.12 comma 5.38. Are you guys on track? Everybody, is it too much to bear? Is it fine? Okay, so I had calculated for centroid, for new centroid for C1 and C2. C1 was 1.83 comma 2.33. C2 was 4.12 comma 5.38. Now what I will do, I will check now whether these points belong to that particular cluster or not. So how will I check? So you can see over here the calculations, the math I did over here. So now based on whatever I did, it is again same. So before we had an ambiguity over here whether 3 belongs to this cluster. Now it is pretty clear that this belongs to the second cluster. Do you understand? There was an ambiguity, right? Initially I put, I took for my choice, I took 1, 2, I thought even though there was 3.61 and 3.61, I could have put 3 on cluster 1 or cluster 2. But what I did, I ended up putting in C1. So I computed the centroid again and checked. So now it's very clear now. So the third individual belongs to cluster 2 because its distance from the centroid 2 is closer. So it is 1.42. So now in our cluster 1, we just have 1 and 2. Rest all are same, I think. Yeah. So rest all cluster 2 has 3, 4, 5, 6, and 7. Okay. Then yeah. So now what happened is again I did manually. I tried doing the math and checking because now is it done? Is this the final cluster? Yes. This is a final cluster. Again, I didn't want to make it too tedious on the page. So I checked again. Now our last step was we had to repeat this. We had to keep on checking until our centroid is the same value. Until the centroid is the same value, we keep doing this. Okay. That is basically we're checking for convergence. That step is called checking for convergence. We just checked for convergence because what we have to do, we have to initially we have to repeat this process until we update the centroid, and the centroids do not change. Okay, if the centroids do not change anymore, the algorithm is set to converge. So again I did the math again. I checked, I computed 1 2. What is 1 2? I think the point was 1.0. Okay, I forgot the points. Let's just go back. Again you can compute the, you can do 1 plus 1.5 divided by 2. Then you can do 1 plus then you can do the math for this thing, 1.0 plus 2.0 divided by 2. So 1 plus 2.5 divided by 2, which is nothing but 1.25. Then it is 1 plus 2, which is 1.5. So again you can compute this centroid and check. Again you have to check compute the distance between each and everything and check whether it is the centroid is changing. So I had already checked for this question. It is not, the final clusters are C1 has only 1 and 2, and C2 has 3, 4, 5, 6, 7. So 7 centroids do not change. What is the assumption? What is the conclusion? The conclusion is the algorithm converges. That means this is your final cluster. Any doubts, guys? Yeah, that is it with clustering. So now Ritika will do the practical part of it. Any doubts in the numerical? Anywhere was anybody had felt any difficulty? I will repeat the whole thing even if anybody tells. Anywhere, any doubts? Okay, Ritika, you can take over. Yep, you can do.
Thank you.
Ritika will be doing the practical implementation.
Yes. Is my screen visible?
Yes, Ritika.
Okay. So all this time we were seeing about cross validation, and we move forward with k-means clustering. So over here we're going to use the same data set, that is the iris data set, and try figuring out how the k-means clustering is going to be incorporated in this. So we're using the normal libraries, that is pandas and numpy for the data manipulation visualizations. Then we're using similarly matplotlib and from the sklearn cluster, we're using k-means algorithm and seaborn for visualization. So first, I'm loading the data set. These are the values. We have seen this before. We have 4 columns: the sepal length, sepal width, petal length, and the petal width. These are the species. In the similar manner, if I want the first 5 records, what do? I use data.head. And if I want the last 5 records, what do? Data.tail. So the last five, so totally from 149 to 145. The last five values, 5 rows that are present will be visualized to us. What is the length of the data? 150, and the shape is 150 comma 6. That is nothing but we have 125 rows. That is 125 rows, and we have 6 columns that are present to us. Now we can see that there's already 0, 1, 2, and then again we are giving ID to it. Doesn't it feel like ID is a bit redundant over here? So what we're going to do is we can drop this ID column. We're dropping this ID column, and then we have the normal values. The this is nothing but the index values. We have the sepal length, width, petal width. The things that are present before it is nothing but the info. What is the information that this contains? We just want to know if it has any null values, what is the data type. We see it's a float 64, and the number of values in each of the columns are 150 over here. Plus, we're doing the describe. As you guys would have seen before, data.describe tells us the amount of count of values that are present. We have under supplements, we have 150, 150, 150 because we have 150 flowers. So automatically we'll have 150 supplements, sepal width, petal length, petal width. We have the minimum maximum values. We see if our data set has any null values. We see over here they're full, false, 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 false. We do not have any null values, so there's no major pre-processing step that we have to do. We can also say it in specific for us to see if we have anything. So we're taking the sum of the columns and we're seeing we have no null values. We have dropped the method. Moving forward, let us go with our k-means clustering. In k-means clustering that we are going to do over here, as Suprata mentioned before, first we need to know how many clusters we should see. To find how many clusters are there, we need to know over here we know we have 3 flowers. So I'm choosing 3 clusters. But is that an idealistic method or an idealistic way for us to nothing but find it? No. We have another method known as the elbow method. Using elbow method, we find out what is the way. Before we move towards it, first let us first find what is the total distance of the points within each cluster to their centroid. Let me do with this example. So first, we'll just consider this as my images. So if we consider all of these are my dots, I want to know from the centroid what is the distance of each of the point to the dot. Each of the point to the dot. I find all what are these distance. Consider this one centroid. The distance of each of the point to their centers. The distance of all the points is what we're going to store these values in a array over here. We're appending these values. Then we're using elbow plot. So what is this elbow that we're doing? What is this elbow method? We're using elbow method to know the number of clusters that we're doing. It is not a safe manner to just assume the number of clusters by seeing the target column. Just because we know that we have 3 flowers, we cannot choose our target column to be 3. We have to use the elbow method. In the elbow method, what are we doing? First, we run the thing, we run our clusters for 10. So we're creating, initially we're considering 10 clusters. In the 10 clusters, we have 10 centroids. What did we do? For each of the centroids and each of the data points. For each of the centroids and each of the data points, we're seeing the distance present between them. And we're storing these values in an array known as WCC. We're storing these values. Then what are we doing? These are all the values that are present. We calculate the average scores for each of the k values and we are plotting them. So we have the WCC values and the number of clusters. For 11 clusters, what is the total distance from the centroid to all the different points that are present? We can see the first value is nothing but very high. But as we move forward, we see the value is nothing but decreasing. This is my idealistic value. Yeah?
Yeah, question
Yeah.
here. You can ask. There's a
Yeah.
bonus question here. what is the K value? Which is the best K value? Guys, bonus question. I'm noting down the names so you guys grasp it. Is it 2? Can you guys check again? It's clearly written. Okay, 3. 6. Hmm. More answers, guys. I'm noting down the people who are answering, even if whether it's right or wrong. 5. Okay, I can see answers from 2 to 5, 2 to 6.
Okay.
It reaches to convergence at 6. So 6, one of them is saying. Okay, more answers. Yes, be interactive, guys. Great. Gia saying 6. Okay. That's all? You don't reach convergence, is it? That's it? Ritika, I can see answers from 2 to 6. There's a
Okay.
yeah. So you reveal the answer, and the person who has got the right
Yes.
answer, or whoever has given the right answer, will get bonus marks. Okay, it's not
So
only
the
one person.
right answer is 3. We can see that after this point over here, this is the main point. We see a curve over here. Initially at 1, it's super high. And then from 1, it starts reducing. It's a drastic decrease. Then from 2 to 3, it is a curve. We can see a curve over here, a small curvish we can see. But then from 3 is the point where it is going stable. It's attaining that stable saturation point. So 3 is the perfect cluster for us to choose, and it exactly aligns with the number of classes that we have. So we choose k is equal to 3. So whoever took k is equal to 3, they will get a bonus point. So moving forward, now we know the number of clusters that we want are 3. Now we have decided the value as 3. So we are now using k-means clustering, and we're using the init class as k-means plus plus. We're using 3 clusters. Now what we're doing is, we are not in a table initially. If you guys remember, this was our data. We had sepal cell length with petal with species. And we also had a target. Okay. We also had the species columns. Now we are not going to use this species values to predict and do our unsupervised learning. What is unsupervised learning that we saw? These are values that have no labels. So we are going to drop this column. We do not know what this column is, and then we are going to see if they are actually predicted or not. So in simple language, what can we say? We can say that this species column is going to be our test data that we are going to predict on, and we're going to train it by using sepal length, sepal width, petal length, petal width. These are the 4 columns that we're going to train it with in order to predict what? The species column. So that is what we're doing over here. So what are we doing? For the clustering data that is present, we're telling k-means to predict the value. Whatever value, this is nothing but predicting, we are going to add it to the cluster predictions that are present, adding up a new column over here. These are the first 5 rows, and this is how this is adding to it. Now, what are our cluster mean centers? As seen before, we have totally 3 clusters. We are mentioning over here that my number of clusters are 3. We are explicitly mentioning it here. So, what are the cluster centers that are present? As we have seen before, Supraja explained how the clusters are being found mathematically. It is not necessary for us to sit and do all the maths behind it. We could just use a simple terminology such as k-means, the KMS cluster centers. We get the 3 clusters that are present. Now we have all the clusters. But how can I know that if these values are present in one cluster or not? How will I be able to see if all my centosas are in one cluster, all my virginica are in one cluster? How will I be able to see 3 flowers? So let's try visualizing it. To visualize it, first I am saying that let my X be the cluster. I'm scattering the plot. That means I'm not using the values in the form of a bar graph or anything. Scatter meaning these will be in the form of dots, in the form of points. And I have cluster predictions. What is cluster predictions? The last column that we have. So I'm telling whichever the cluster predictions are for. So we have 3 cluster predictions. If cluster 0, then it is Sentosa. What are the 3 flowers that we had before? We had Sentosa, Virginica, and the other flower. So I'm putting 0 to the first flower, 1 for the second flower, and 3 for the third flower. So I have 0, I have 1, I have 2. 0 for the first flower. And what am I saying? I want the sepal length. I want the sepal width. So I'm predicting using sepal length and sepal width. What is the label I'm giving? I'm giving iris versicolor. That is the color. That is the name of the flower. Then I'm telling that if the cluster prediction is 1, take its sepal length, take its sepal width, give a label of iris centosa. I'm giving colors for this. I want my first cluster to be teal color. I want my second cluster to be in lime color. And I want my third flower or the third clusters. What am I considering? I'm considering its sepal length. I'm considering its sepal width with a color of magenta and a label of iris virginica. Now, using all these that are present, I am plotting it. So these corner elements are known as the legend. So we are specifying what and all things should be coming to the legend as labels over here. So we can see from this thing that when we put clusters are equal to 3, it has perfectly almost classified that this is one cluster, this is the second cluster, this is the third cluster. So Iris virginica is the third cluster, Iris centosa is the green, light green teal cluster, and Iris versicolor is the dark green cluster. The yellow points are the centroids that are present. What are we taking into consideration? We are using the sepal length and the sepal width and the length to find these clusters, to find which cluster each of the flower begins. Now, what do we know? We know that we have three clusters, we have three flowers. So these exactly coincide with the clusters that we have formed. Yes, so this is the
Shall we
last
put
ending
6
for
and
the
6, Ritika? Let's put 6 because people said that k should be equal to 6. Let's see what k equal to 6 gives us. Do you have to run the model again?
Yeah, I have run them online.
Okay. Yeah, if it's k equal to 6, it is going to be really haphazard. That is, here we had 3 flowers. We had to classify only 3 this thing. So it had given correctly the 3 of the flowers, which is Virginica, then we have Sentosa. So it had correctly classified them into 3 different clusters, and then they had given the particular centroid. Yeah, that is it. Okay.
I would run the model also. I have no problem. It will just
Okay.
take a minute.
Iris is on top. Yeah. Guys, any doubts in what Ritika or I had explained?
Yeah, by the time we run all this, you guys, if you have any
Yeah.
doubts, you can move forward with
Yeah.
it.
Anybody has got any questions? Even the simplest of the question will be answered. Please do not hesitate. Anywhere, the numerical was not clear anywhere. I think everybody is clear. No,
I
that
should
that
run
will.
all the things from the
Yeah,
starting. This
yeah.
is going to take some time. Yeah,
Yeah,
I
we'll
I will
share the
probably
model with
update
you.
it. Yeah,
Yeah,
yeah, I'll probably update it and then we will share the model.
yeah. We'll share the model with you. You guys can experiment with whatever Ritika has done. Yeah. Abhinav, can we conclude?
Yeah, sure. So a very nice and informative session by Ritika and Supraja. Thank you for it. I think
Yeah.
I hope all of you enjoyed it and learned new things. If you have any doubt, please feel free to reach out to any of us. There's also a doubt group uh, where you can ask your doubts or reach out to us personally.
Yeah.
And a lot of you have not are not submitting your assignments. So please submit it on time and remember to press the turn in button, or else we won't be able to check your assignments. Anyone? Okay, I think there is no doubt.
Yeah. Okay. I
Fine.
shall take my
So
leave. Yeah.
let's
Thank
conclude
you.
today's sessions. Thank you everyone for joining. We'll see you again next week.
Thank you.
Thank you.